Yesterday we did multiplying powers and raising powers to powers, and now we're doing division of powers. Okay, and just quick review, the base is the number you're multiplying by itself. The exponent is just an instruction telling you how many times to multiply it. And that whole thing together is called a power. And as long as you remember the definition of an exponent, what it is, that it's not a quantity in the problem, but rather an instruction or an operation, then there's really nothing you need to memorize about exponents, okay? So the first thing we're going to do is just divide powers, but if we follow the rules we did yesterday, there's really nothing more challenging here than there was about multiplying powers. So a to the fifth is a times a times a times a times a. I got 5 of them. A to the third, a times a times a. But notice what's going to happen. A over a is just 1. So 1 times anything doesn't change it, so I can get rid of that. I also get rid of that, and I can also get rid of that. So the only thing left after I do that division is just a times a in the numerator. So if I wanted to write it, I could take an extra step and say that's a squared over 1, but that's just a squared, right? That's in the numerator, okay? Next one, negative 3 to the 7th, negative 3. Put these in parentheses, negative 3. That's 3, that's 4, that's 5, that's 6. That's a lot of negative 3's. And then over 3 of them. We're multiplying 3 times now, okay? Those are going to cancel out. Those are going to cancel out. Those are going to cancel out. What's left are 4 of them, all in the numerator. So you're going to have negative 3 to the 4th power. And notice I'm not going to bother writing over 1 that time, but that's really what's happening there. Okay, so let's look at what happened. We had 5 in the numerator, 3 in the denominator, and we ended up with 2 in the numerator. We had 7 in the numerator, 3 in the denominator, and we left up with 4 in the, so 5 minus 3 is 2, because when we were canceling them out, we're really subtracting. So 5 minus 3 is 2, 7 minus 3 is 4. And so the rule is, if you're into that sort of thing, if you have a to the m power divided by a to the n power, you're going to be left with a to the m, whatever that number is, minus n, whatever that number is, and that's it. So let's do a couple little more complicated versions, right? So 5 to the 8th times 5 to the 2nd on top, I'm going to simplify that. And I could write out 5 times 5 times 5, 8 times, and then times another 2 times. But I'm just visualizing I have 10 of them on that numerator. So I know I'm going to have 5 to the 10th up there over 5 to the 3rd. And I know, again, I'm imagining the 10 5s on top and 3 on the bottom. And so 3 sets are going to cancel out. And what will be left is just 5 to the 7th in the numerator. And if you're not sure how I got that, just draw them all out. Draw all 10 5s in the numerator, 3 in the denominator, and see what you get left after you cancel out. So down here, we have a fraction and then one that's not a fraction. So I'm just going to write that as a fraction over 1. And so now I get 1 times x to the 6, which is just x to the 6. And I get x to the 4th times 1, which is just x to the 4th. And that is just x squared. And again, if you're still struggling with that, just write them all out. X times x times x 6 times over x times x times x times x 4 times, and you'll end up with just the 2 in the numerator. All right, so now we're going to raise these quotients, which is a division problem, to a power. So let's just see what happens. We get a over b, but I got to multiply that 4 times because that exponent applies to the whole quantity inside the parentheses. So a over b, a over b. And notice I just get a times a times a times a in the numerator, just a to the 4th, and b times b times b times b, which is b to the 4th in denominator. So let's do one more and we'll see sort of the pattern that's happening. So again, the whole thing, negative 7 over x, I have to multiply by itself 2 times. And so in the numerator, I'm going to get negative 7 squared and then x squared. And if I want, I could say negative 7 times negative 7 is positive 49 over x squared. So notice what happened in both cases. The a got raised to the 4th power right there, and the b got raised to the 4th power. And then here, the 7 got raised to the 2nd power, and so did the x. So the rule, if you have a divided by b and you raise it to the m power, it just, what's going to happen is both parts of your quotient are going to get raised to the m power. You'll just have a to the m over b to the m. So let's apply that a couple places, right? So I could write this whole thing out if I wanted, but I just know that I'm going to end up with 4x squared multiplied by itself 3 times, because this exponent is going to apply to both. And I'm going to have 5y times 5y times 5y. So 4 times 4 is 16, times 4 is 64. X squared times x squared times x squared. If I write them all out, I'm going to have 6 of them. That's x to the 6. 5 times 5 is 25, times 5 is 125. And y times y times y is y to the third. And since x and y are not like terms, I can't simplify those. All right, again, down here, I'm going to need to deal with, and sorry, this should be a squared. That should be an exponent. So I'm going to have a squared over b, and I'm raising that to the second power. So I have to deal with that, and then we'll multiply that by the fraction. So let's take this in 2 steps. So the first thing I'm going to say is, well, that's a squared times a squared over b squared. And then I'm going to multiply that by 1 over 2a squared. So a squared times 1. I could combine that right now if I want, or I could just write, well, that's just a squared times 1. That doesn't really do anything. I'll just leave the 1 out. Over b squared times 2 times a squared. And see, I can write the pieces in any order. I could have wrote 2a squared b squared if I wanted. That doesn't really matter. What matters right now is we're trying to cancel out, right? And I know that a squared over a squared, I can cancel that out. So what I have left in the numerator is just a squared. And the denominator, I could write b squared times 2, but I'm just going to write 2b squared. And that is that. Last problem. And this is just applying the concept of orders of magnitude that we did yesterday to this dividing powers. So the luminosity in watts of a star is the total amount of energy emitted from the star per unit of time. The order of magnitude of the luminosity of the sun is 10 to the 26 watts. The star Canopus is one of the brightest stars in the sky. The order of magnitude of Canopus is 10 to the 30 watts. How many more times luminous is Canopus than the sun? So all they're asking me to do is just compare them. I'm just comparing, right? I'm writing a ratio. That's a comparison of the brightness of Canopus, the brightness of the sun. And notice, if you wanted to write this out, you'd probably need another piece of paper, right, to write 10 times 10 30 times. But in the numerator, imagine 30 times, 10 times 10 times 10 30 times. And then in denominator, 10 times 10 26 times. And after you cancel out the 26 pairs, you will have 4 10s left in the numerator. I could write it like that, but eventually it's just 10 to the 4th. And remember, 10 to the 4th is 4 zeros, so that's 10,000 times brighter. So it's quite a bit more luminous.